All right, so let's come back. So I think there is an interesting questions in the chat box. Is okay. As in this example, we say this ISR 0 vector is 4 byte. And why this is 4 byte? So the reason is this assumption is we run on a 32-bit systems. Okay, so on the 32-bit systems, like for the code segment and instruction pointer, they both will combine together, and then the size will be 4 byte. Okay, 4 byte means 32 bits. So each code segment plus instruction pointer, it will occupy 4 byte. Okay, so this is the reason why this is 4 byte, not other bytes. Okay, but I mean, this is a concept. I mean, if we're in a 64-bit systems, it might not be 4 byte, but like even it is larger, it doesn't matter. Then the thing is just like if it is larger, then this step interrupt vector number will times a larger kind of number here. Okay, so this is just for a positioning about where is the instruction pointer is. Okay. So so let's get going. Like there are first fit, best fit, and worst fit, and then how to know how good they are. So actually there is a thing called fragmentation. Like if you doesn't really do a good allocation, or like if there are some like long-term, like when you use a system for long-term, then probably there will be some places they cannot be used, and that is called fragmentation. So the first one is called external fragmentation. So external fragmentation means like you have enough total memory space to satisfy a request, but the available spaces are not contiguous. Okay, so it means like, for example, you have if processor one look at this slice, and processor two has this size, and then we have the third process, and maybe it only needs this size. And actually the white part, the summation of white part can fit P3, but because we don't have contiguous space, so P3 cannot get the space. Okay, so this is called external fragmentation. And oh, sorry, I think there is a very important thing I didn't let you know is when we are doing this kind of addressing things, this memory management things, actually each patch frame should be continuous. So this is the reason like this. Each patch frame, they should be on the physical address, they should be continuous. So for example, this patch frame A, they cannot be split into two other patch frame. Okay. So the reason that should be contiguous is it will be easier to be addressing. And it is easier to get where it is. Okay. If this is not continuous, then we need extra management overhead. For example, we need another data structure to keep track of where is the another like their related patch frame is. So this should be continuous. And also for the virtual address space mapped to this physical address space, that should also be continuous. Okay, so for a patch, both the virtual address space and physical address space should be continuous. There should be a continuous 4 kilobyte area. Okay, so this is very important for the design of the pageant. Okay, so this is called external fragmentation, and internal fragmentation I think is quite easy. Just like it occurs when systems split the continuous space into continuous chunks. Oh, sorry. For example, like if we have a like 4 KB area, right? But actually inside the 4 KB, you only store like 3 kilobyte of the space, and you let 1 kilobyte there. Then this is called internal fragmentation. Okay, so this happens even you are using pageant because each page is 4 kilobyte. So if you use, I mean, if the data is smaller than 4 kilobyte, then there goes the internal fragmentation. Okay, so if you are going to solve the internal fragmentation, in most cases, you need a smaller page size. But smaller page size means you need more overhead to manage it, right? For example, coming back to the patch frame overhead. I mean, this patch frame, each patch frame is 4 kilobytes, so they have those kind of fields here. So after some calculation, we know we need 40 bytes to manage this 4 kilobyte area, right? But if you string the patch size to only 1 kilobyte, then the size is also 40 byte. But for this 40 byte, you can only manage 1 kilobyte. So the overhead will become 4 times larger. Okay. So the reason why we care that much about this is 40 byte because this structure should be also put on the memory. So it also consumes memory. And this 40 byte is just about, I mean, they're just here, few counters here, but in the real system, if there are more counters, then 40 byte will go up. Okay, so it really takes some overhead if we shrink the patch size to a smaller patch size. Okay. Okay, so this is for the external and internal fragmentations. Okay, so I think those are about the things we learned in the undergraduate. And now let's talk about how Linux manage this kind of physical address. So actually, Linux manage this kind of physical address in a little bit different way. So first of all, we need to define a thing called zone. So the kernel uses the zones to group patch frames or similar properties things together. So like this. Usually there are 3 kinds of zones in Linux. The one is called zone-DMA, and then zone-normal, and zone-high memory. Okay, so zone-DMA, it is about the very beginning of the memory, like it is between 0 megabyte to 16 megabyte. Okay, so zone normal is about 16 to 96 megabyte. And then zone high memory will be larger than at 96 megabyte. Okay, so maybe you will be quite curious about why we're going to split the zone into this kind of different property things. And this is because in the old systems, I would say like maybe 20 years ago systems, actually DMA is quite very, I would say like spatial settings there, because for some DMA settings, they can only support the first 16 megabyte of the memory. For example, if you are going to move the data, like the networking data to the host systems, and if you use DMA in the old system, you can only use the first 16 megabyte of the host memory. You cannot use more than that. The reason is because in that times, the DMA, the DMA is a hardware design, but there is some register inside the DMA. So there are some limitation there. You cannot flexibly use the whole host memory. Even you have like 16 gigabyte, you have like 64 gigabyte there. But at that time, when you are using DMA to move the data from storage device or like network device to the host memory, you can only use the first 16 megabyte. So due to this reason, at that time, Linux say, in this case, let's allocate, let's reserve the first 16 megabyte for this DMA usage. Okay, so this is the reason why we have zone-DMA. And zone-normal, you can think about most of the kernel related code or like most of the kernel related information, they will be placed in this area. So this is about the top. If you still remember, when we're using the 32-bit systems, kernel will use the top 1 gigabyte of the virtual address space, right? So this is the SAM. The zone-normal, they are alluding, they are saying from 16 to 96 megabyte as for kernel data structure. Okay, but we'll talk about this a little bit more later because I think this is quite complex. So you can just think about, hey, now zone-normal is for kernel, and zone-high memory actually, this part of memory just like more than at 96 to whatever your system is. Just like if it is a 16 gigabyte and this will be at 96 megabyte to 16 gigabyte, then zone-high memory, like those kind of memory space, they're allocated to zone-high memory. And the reason for why it is called high memory is because the lower 1 gigabyte, they are preserved for the, the upper 1 gigabyte, they are preserved for kernel. So the rest of it, they are for the user process. Okay, And there are more details later for this part. Okay, so here are the explanation about what's the function for each kind of zone is. Okay, so the second thing you need to know is there is a concept called node, and we will put the zone, node, and patch together later. Okay, so the reason why Linux needs the concept of node is because in current system there are two different ways to access the memory. One is called uniform memory access. The other is called non-uniform memory address. So maybe you heard about it called NUMA. Okay, so uniform memory access just like this. So in the very traditional systems, like at that time on the motherboard there is a node bridge. So on node bridge there is memory controller, and memory controller can help the CPU to access the DRAM. Okay, so this is the old system. You can think about maybe like 10 years ago or like more years ago. And then current system, they move the memory controller into the CPU. Okay, so it looks like these kind of things. Just like each CPU has their own memory controller, and then they can connect to the DRAM. Okay, but the thing is, actually the CPU on the left-hand side can still access the DRAM on the right-hand side, right? And the way to get the data from the DRAM on the right-hand side is CPU on the left-hand side will first communicate with CPU on the right-hand side, and then to say, can I access your DRAM? And then after getting the permission, CPU on the left-hand side can access the DRAM on the right-hand side. So this is called NUMA because it is non-uniform memory access. For this CPU, accessing DRAM on the left-hand side is faster than accessing DRAM on the right-hand side. And the latency gap usually is kind of 2 times. The reason 2 times is because, first of all, CPU needs to talk to all CPU. And then the DRAM, the data should be moved from one CPU to another CPU. So it takes a little bit higher overhead here. Okay, so there is local access and remote access here. And maybe you are thinking about why we are going to move from a UMA system to the NUMA system. There are several good things for NUMA. First is about it has faster local access because this DRAM is directly stick with this CPU. Okay, so the bus is shorter. But if you look at the left-hand side, the UMA system, actually here comes a bus and here comes another bus. So usually there are 2 buses. So when we talk about the data transmission, when the bus is longer, when you have more bus to get to the destination, then you will get longer time. So shorter bus always get better performance. So this is the reason why when you have a CPU in the systems, and then you usually place your DRAM near the CPU. And your SSD usually will use like the PCIe, these sort of things to connect to it. And PCIe is longer than DIMM, right? Because DRAM DIMM is stick very close to CPU, so they can get better performance. Okay. And then NUMA can have better bandwidth. So the reason I have better bandwidth is because on the left-hand side part, this memory controller should control all these kind of DRAM requests. So you can think about if there are a million requests to be sent to this DRAM, then this controller should take care of this kind of million requests here. Then this controller will become a bottleneck here to manage this kind of service. Okay, so this memory controller you can think about just like a very tiny CPU to do some decision about if the CPU 1 is going to get the data from DRAM 1 and CPU 2 is going to get the data also from DRAM 1, then how do I do the scheduling? Okay, so actually this kind of memory controller here will do some scheduling things, and then it's going to avoid some like package congestion later. Okay, so yep, that is about NUMA and UMA. So nodes compute like this. So nodes maintains a data structure for each NUMA node. So one NUMA node you can think about just like one CPU. So in here there are 2 NUMA nodes. There's one CPU and there's another CPU here. Okay. So first of all, when we are going to allocate the memory, actually we need to be aware of this structure, right? Because we know the DRAM near the CPU get faster time to access it. So when CPU needs the memory, usually we need to allocate this DRAM to the CPU, right? Otherwise, if you allocate this DRAM, it is also possible, but it takes longer time to access it. So node is quite important here. Okay, so let me give you a overmap about what's the relationship between nodes, zone, and patch frames. So nodes will be at a very top tier because each node we need to allocate the DRAM nearest to inside each node. Okay, so for example, for this node, we will allocate this DRAM. But I mean, if this DRAM doesn't have enough space, then we will allocate other DRAM. Okay, but actually, this is only 2-node systems, and there are some server that will have 4 nodes or like more nodes there. So the network topology will become more complex if there are more nodes. So we need to manage in a node aspect first, and then it's zone. So you can see like for each node, under each node, there are 3 different kind of zones. Because for zone DMA, this is for very spatial usage. They're only for DMA usage. So we cannot allocate the first 60 megabyte of the DRAM. So we need this kind of zone concept to manage these kind of things. Okay. And then under the zone, there's patch frames, right? Okay, so because zone is usually larger than like the patch frame, this kind of granularity. So this is the hierarchy for the Linux to allocate the physical memory. Okay. So question. Okay. So let's talk about how to allocate the patch frame. So actually, Linux doesn't really use best fit or like first fit or worst fit. Linux use things called body system to allocate the patch frames. Okay, so there is a function in Linux is called allocate dash patches function to allocate a single patch or more than one patch to the process. Okay, and if you have some sense about Linux, actually there are also bite-size allocations, and they're using some other kind of functions here. But I think there is a kind of overall picture about the memory allocation. So usually we will split the application into 2 sides. One is called user space memory allocation for the user process, and then there is a kernel space memory allocation for the kernel side. Okay, and there is a physical DRAM here. So usually there is a allocate patches layer here, and this layer they are using body system. So this is people will say like this is a low-level memory allocator. So we can get like single patch or multiple patches at this layer. Okay, so above the allocation layer here. For kernel, actually they can use 2 different sizes to do the allocation. One is about the K memory allocation. You can get a smaller size, or you can just directly get from the allocation pages. Okay, so there is a thing called step layer, and we'll talk about it later. Okay, so there is also another thing is if the kernel is going to get a larger size from the physical DRAM, we can use this kind of V memory allocation. Usually we're going to allocate like several megabyte or like gigabyte, and then we can pick this kind of virtual memory allocation. Okay, but the things that you know is for most of the kernel data structure, in most cases, we will go for this K memory allocation. So what do I mean? If you still remember, here, this is one data structure in kernel. And I said this is a structure pages data structure, and there's 40 byte right. So this 40 byte, if we are going to allocate a place to put this data structure, usually kernel will use this K memory allocation function to allocate a 40 byte to store those structured patch. And the same things, I mean, if you already learned about like text structure, data structure, those kind of data structure, they are also using K memory allocation to get the memory space to store those data structure. Okay, so there's another branch is a user process. So user process, they will use, I use C library here, but I mean, there's other kind of compiler, they do the very similar things. So for the C compiler, C library, actually there is a memory allocation function here. And then there are two different ways to get a memory. One is called mmap, another is called BRK. So both of the function can get the memory. So usually when we are going to get a larger memory space, we'll use mmap. And if we are going to use like heap, these kind of things, usually we'll go for the BRK. Okay. So let me focus on the allocation pages now. So actually there is a list here, and let's directly look at the example. If a process requests a 2 to the 2 blocks, so you can think about if a process needs 4 pages, but there is no free pages in order 2 and order 3. Okay, so this order actually means like 0 means 2 to the 0, so a 1, and 2 to the, and 1 is called mean 2 to the 1. Okay, 2 to the 2, 2 to the 3. So like this. So for each block means like for each 4 kilobyte pages. And then if we are going to get 2 to the 4 means with this layer, there are 16 pages here, right? So if there is no patch in the 2 to the 2 here, and there is also no in the 2 to the 3, actually the body system will get from a larger order. So we will always get a larger block and then to split into the half for the allocations. So if we are going to get 2 to the block, like 4 pages now, and there is no free space in order 2 and order 3, then we will get from order 4. So inside order 4, when we do one allocation, we will directly get 2 to the 4 block. And here, block and page, they can use interchangeably. So block means pages. So for the level 4 here, actually, kernel will directly get 16 pages directly. But we will break this 2 to the 4 to half. So you can see like after breaking into half, we will keep 2 to the 3 at the order 3 layer. And we will allocate another 2 to the 3 to the lower layer. So the left-hand side of the 2 to the 3 will be kept in the order 3 layer. And then the right-hand side of the 2 to the 3 blocks will be moved to the lower layer. So this is 2 to the 2. Okay. So because the 2 to the 3 can be breaks to 2 to the 2 blocks. So after these iterations, if the system is going to get 2 to the 2 block, the system will directly return these 2 to the 2 blocks. And at this moment, in the body system allocator, in order 2, we have 1 2 to the 2. And in order 3, we have 1 2 to the 3. And then in order 4, like there is no, because they are allocated to the lower level. Okay, so we always get a larger one and break into half and then to do the allocation. So the reason like we also do the half allocation is because it is easier to do the maintenance. Okay, what I mean maintenance is, for example, if we are going to deal with the fragmentation, this will be an easier way because they are all following the 2 to the order mechanism. Okay, so you can think about if now we are not using this 2 to the order, like you can get any size, then probably there will be a lot of external fragmentation there. But if we use this kind of 2 to the order, probably we can alleviate the fragmentation issues because they are all in a block of the patch size. And then they are all half and half and half. So you always can get a larger one, and then our larger one can always break to the a fixed size of the lower one. Okay, so this is the way like Linux thinks it is possible to deal with the external fragmentation by this kind of body systems. Okay. Okay, so there's another concept is about step layer. So step layer is here. This is step layer. So the location pages, we use body system to always split the larger blocks into half and then to check if it fits for the request or not. If it doesn't fit, then we will split into a smaller one. Okay, so when we go one layer above the allocation pages, there is a step layer for the kernel side. Okay, so what does step layer for? So actually, step layer is for storing those data structure that is no longer needed is returned to the free list instead of deallocated. So let me give you an example. Okay. So one cache is for like process descriptor, for example, and there is maybe another cache, maybe is for the file object, and the other is for the like a structured cache. So different cache in the slab there, it means it is designed for different data structure. Okay, because different data structures, they have different sizes. For example, process descriptor maybe is in the size of the 100 byte, and file object maybe it is in the size of the like 10 of the 100 bytes, for example, like this. So different data structure, they have different sizes. So we need to have different like cache to deal with it. Oh, this cache is not equal to like CPU cache. No, they're not the same. This cache is just defined by step there. So step there define their cache structure. And here, so this is the text structure, if you still remember. And then actually, if you check the Linux kernel, there is a semaphore data structure like this. So actually, in a slab there, each cache can maintain one data structure. So each cache, maybe there is a lot of process descriptors, then you can think about the cache will be quite large, and they will have spaces to put each of the process descriptor on the memory. Okay, so this is the inode. So actually, different kind of data structure, they will have different sizes. So this is the reason why they are split into different cache. So, okay. So when the available memory is low, there is no way for the kernel to communicate to every free list that it should shrink the size of its cache to free up memory. Okay. So slablayer acts as a generic data structure cache in there. I think this sentence is quite important because for using slablayer, actually, when you can think about when we are going to deallocate one process descriptor, right? If one process is terminated, then at the end of the termination process, we will clean up the process descriptor. But for example, if this one is like 800 byte, and we deallocate this 800 byte, then actually, if next time we are going to use up this 800 byte, it will be not easy to use because different data structure will not really fit this 800 byte usually. Then there will be a fragmentation. So an easier way is let's just keep the 800 byte for the next process descriptor because each data structure, they will be in the same size. So no matter which process, their process descriptor, for example, will be 800 byte. And for no matter which file, their file objects will be in the same size, for example, 100 byte, for example. Okay. So different data structures, the same data structures for different process, they will still have the same size. So the key concept behind the slab there is to be used as the generic data structure cache in there to cache in different data structure. And the reason like Linux wants to have this kind of design is because frequently used data structure tends to be allocated and free often. So if we can have this kind of caching-like design, then we don't need to worry too much about the fragmentation. Okay. Once again, this cache is not CPU cache. So this cache is just defined by step there. Okay, so they're different. Okay, and there's another reason why we need this kind of generic layer is because kernel data structure is usually smaller than a patch because patch is still too large for the data structure. Patch is 4 kilobyte, but data structure, the size is varied, but probably it will not larger than 1 kilobyte usually. It's just several bytes there. Okay, so frequent allocation and delocation can result in memory fragmentation. So if we can maintain this kind of slab layer, we can deal with this memory fragmentation issue. And also this step layer can be met per processor. So no locks are required for allocation and deallocation. And it also can be NUMA aware, like these kind of things. Okay. So how slab layer works? So the key idea for the step layer is to avoid from allocating and freeing up physical address as frequent as possible. So actually, the structure will look like this. The structure is cache, slab, and patch. So one cache per object. So for example, what I mean object is, for example, for text stack structure, inode, semaphore, they will be classified into different cache. So there is a text structure for getting one cache, and under this cache, they can have a lot of text structure related to belonging to different process. But this cache cannot be used to store, to accommodate the inode or semaphore. Okay, so inode has their own cache. Semaphore has their own cache. Okay, so like this. And okay, so inside this cache, there are several lists. There are 3 for them. One is full, and then partial, and then free. Okay, so full is like this, just like for the patches, they are used for this slab cache, and they are in this patch, there will be partition to split into this kind of text structure, right? Because each patch is 4 kilobytes, but each text structure probably will be like only several hundred bytes here. So in each patch, we can store several text structure inside. And what we call full is if there is no free space for a new text structure, then this is the full slab. So there are use. Okay, so what do I mean for partial is when there are some text structure, they are deallocated or like they're unused, because if there are some process that are terminated, then the corresponding text structure will be unused. Okay, so actually when one process is terminated, we will not delete, we will not remove the text structure right away. We will leave it. We will just mark it as unused. And then if there is another process, if there's new process, they are forked by their parents and they need a text structure, they can directly grab a space from the partial and they can directly use it. Because they are all text structure. The only difference is for the field in the text structure, they are quite different. So the difference will only be maybe for the first field, previously it stores like 1, and then for the second field, and then for the next process, the field will be changed to store like 2. So the layout for the data structure is the same. The only difference is just the value for each field is different. So it is possible to directly reuse the space. Okay. So actually there is a scenario is if for this lab, actually there is called empty list. It means like all of the text structure inside there are unused. Okay, so in this case, it is possible to have one choice is to directly reclaim this lab. It means like all the text structure there becomes unused. So maybe we can directly erase or like to deallocate this memory to other usage. Okay, so this is the concept for this kind of slab there. Okay. So for the allocation, only when there does not exist any partial or empty slab in each cache, we will do a new allocation. Otherwise, if there are some like partial or like empty, and we can just directly reuse those space. We don't really need to do a new allocations for a slab there. Okay. Okay. So, so when we free the slab, only when the memory utilization is quite low, and then there are this kind of empty slabs, then we will free up this kind of empty space. Otherwise, if the memory kind of, we still have enough memory in our systems, we will not do the free. Okay, because just put it there, and one day if there is process they are created, we can just directly reuse this text structure. We don't need to do the construction there. Okay. So it will save sometimes, because if each time we do the fork and we are going to do copy on write, and after copy on write, we are going to construct a new text structure, we need to do the allocation. We need to ask for, hey, is there any free space to construct this text structure? So it usually takes time. But if the text structure are already here and we can just reuse them. Okay. So later on is like the two kind of memory allocation provided by the kernel. One is called K memory allocation, kernel memory allocation, and the other is V memory allocations. So K memory allocation function obtains like kernel memory in bite-sized chunks. So there's just a note, just like to let you know, as you already saw in this figure, like what you usually see is memory allocation is on the user side. So when you are writing a kernel function, when you are writing a kernel drivers, these kind of things, there's no memory allocation function there. You need to use either this one or this one. Okay. So, okay. So if we need a full 4 KB page, allocated page in prior slice fits better. And it returns a pointer points to a block of memory that is at least the requested size for when you're using these K memory allocations. But I mean, if you are going to get more of it, then you can use this kind of, sorry, if you are going to use a smaller one, not like 4 kilobyte, you can use this K memory allocator. Like they will call a step function to help you to do the memory allocation. So K memory allocation in this figure, it works with the step there. Okay. And then V memory allocations is like this. It allocates memory that is only virtually contiguous. Okay. So it requires patch table to maintain a mapping between virtual and physical address. Oh, the reason I say virtually contiguous is not like you can allocate a size smaller than 4 kilobyte. I mean, it is, if you want like 40 kilobyte, for example, then you have 10 4 kilobyte pages. And these 10 4 kilobyte pages doesn't need to be contiguous. Okay. They can be in different, I mean, address space. They can be in different space because we have a patch table. The patch table can keep track of where is the patch is. Okay. Okay, so actually just like allocate virtual memory initially and then map to the physical memory on demand. It's quite the same as the user level things. Okay. So regarding performance, memory allocation inside kernel usually use K memory allocation. So the reason is K memory allocation, in most cases, it's just about to reuse the prior slab. So it doesn't really need to really do too much of the allocation and maintenance. But if you are going to use these V memory allocations, then there's the patch table things here. We need to manage the patch table. So it takes way more time than K memory allocation. So I'll give you an example about how K memory allocation works in the next slide. So if system can get enough continuous physical address all the time, then there is no address translation overhead. So what does this sentence mean? So it means like if the space of the if the space of the virtual address space and the physical address space is in the same size, then we can directly do one-on-one direct mapping. We don't really need a patch table there. And the reason why we need patch table is because virtual address space provide us to use the space larger than physical size, right? So you can think about when you are writing a program, you don't really need to care about what is the size of the physical memory, right? So when you are writing the program, you don't really need to care about how many users are there in the systems. But come to think about it, even each process in a 32-bit system, you can get 4 GB of the virtual address space. But if there are like hundreds of users that have hundreds of processes there, then can each process still get 4 GB of the address space? It is not possible, but virtual memory, that is possible, right? So this is the reason why when you are writing a process, you don't really need to care about how many users are there. Okay, but if you still remember, kernel address space that share between user address space, right? Because kernel used as the top 1 GB of the memory address space. So no matter which user process, they will allocate their first top 1 GB for kernel, and this is quite important. Okay, So why it is important here? So let me show you. So on a 32-bit system, what if the kernel consume more than 896 megabyte of memory? So before answering this, let me show you one thing. So this is virtual address space, right? When you are writing a C program, actually what you can get from memory allocation, those kind of things, they are from virtual address space. Actually, you don't really know what is physical address space because physical address space, they are masked from the user. Only the DRAM controller can know what is the physical address space is. So for this virtual address space, actually the top 1 gigabyte is for kernel. So actually when you are doing the programming, you cannot really program this part because this is for kernel. So when you are programming a C program, you can only use the bottom 3 gigabyte. Okay. So for this top 1 gigabyte, actually from 3 gigabyte to 3.896 gigabyte, they will use K memory allocation, and usually kernel code and data, they are placed here. Okay, so why it is like this? Because this space will directly one-on-one mapping to the physical address space here. Okay. So because all the process, they are having the same location like this. So actually this one can directly map to the physical address from the very beginning, 0 gigabyte to 896 megabyte. Remember, when we are talking about like we have zone-DMA and zone-normal, actually zone-DMA means the first 16 megabyte, they are zone-DMA. Okay, and then from 16 megabyte to 896 megabyte, therefore zone normal. Okay, so even this example just for 4 gigabyte, but you can still thinking like, if this is a 16 gigabyte or like 128 gigabyte, the first 16 bits, they are still for zone DMA. And then later on zone normal, there will be for the kernel function. Okay, so why this is so important here is because here, this one is at 96 megabyte. And this one is also at 96 megabyte. So the virtual address space is in the same size of the physical address space. So we don't really need two complex patch table here. We can do one-on-one mapping. What do I mean for one-on-one mapping is like this. We can do direct mapping. Physical address equals virtual address plus some offset. Okay, so this is virtual address. So actually, if we do add some offset, we can just ship to this. What do I mean for apps offset? You can think about maybe just like to minus 3 gigabyte. So here, if we minus 3 gigabyte, all the address can be directly mapped to this, right? And we don't really need to check what kind of patch table is actually. I mean, there do have a patch table, but it won't be very simple because just like every address, they just minus 3 gigabyte. And for this address space, you can be mapped to here. Okay. So why we are doing like this is because when you are running a kernel, you don't want to take too much of time to run the kernel. And if each time you need to do the patch table translation, each time you need to check the TOB, it will take a lot of time. But now, if you can just, CPU can directly calculate, okay, where is the physical address is, and you don't really need to touch a memory, actually it will save a lot of time. So this is one of the reasons why in Linux, they design their kind of kernel space, they should be shared between all the process. Okay. So there are still like 128 megabyte they are not used. And they're not used is because this 128 megabyte, they are used for dynamically mapped to the rest of the high memory part. Okay, so for physical memory, we only use at 96 megabyte for the kernel code, and all the process they share this at 96 megabyte, but above at 96 too. Depends on how many memory you are using in the system. It can be 4 gigabyte, it can be like 64 gigabyte, or like it can be more. I mean, there's a large memory space here, right? Large physical address space. So probably we need some translation there, right? It cannot be one-to-one mapping because it is not possible to do the calculation. So we need to have some way to do the like patch table management to know, okay, so where is the data is in the high memory part. Okay. So high memory is not permanently mapped. It can be temporarily mapped to here, zone high memory. So for each virtual address space, they have 128 megabyte of this space to do this kind of virtual mapping. So how to use this kind of high memory in Linux? Actually, just about to set out a flag in the allocator. So there is a gap-free patch high memory. Then we can have this kind of this flag can be set at a V memory allocation. Then you can allocate for the high memory. But actually, the thing is like this. Actually, this is because in 32-bit system, we only had 32-bit virtual address space, right? But in a 64-bit system, actually, we have 64-bit virtual address space. 64-bit means you have several gigabyte to or even terabyte of the address space for mapping. So actually, in current 64-bit system, we don't really use this kind of high memory because you have way more kind of address space here. But I mean, this is just quite interesting to let you know at the history why Linux is going to use this kind of 1 gigabyte space and how to place this kernel here. Okay, so yep, that's it for it today. So see you guys next week.